If I have this function and I start with a line tangent, why wouldn't I stop following this line if I realized that my curve was starting to extend upwards? So what he meant, or what that means is, instead of continuing to go further and further away from that curve, once I realize I'm getting further from the curve, why don't we stop? So let's stop following the red line. If I know that the curve is going to start to work its way upwards and my line is going to continue on that same trajectory, why don't we then stop right here, figure out what this new point is, and then think about, well, what direction is my curve heading in now? And while it's not a line tangent, I could use this new point and then whatever the slope of the curve is, and I could now actually write a line through this new point that would have the same slope as this one, because this one now would stay a little bit closer to the curve than the red one would. But along those same lines, if I know my curve is going to continue to increase very quickly and this green line is going to continue to drift further and further away, then why would we then want to stay on the green line? Let's put a stop at some point once we realize we're getting further and further away from the curve. I don't know if I have any other colors available to me. Oh yeah, there we go. We'll go pink. Then let's stop at this point and reassess. Let's figure out the direction the curve is going at this point, and let's go in that same direction with a line, because now that pink one will stay closer to the curve than the red one and the green one. So instead of just staying on that line and getting further and further away from the curve, if we know they're diverging and getting further away from each other, let's readjust, let's stop, let's start a new line that would keep us closer to that curve for a longer period of time. All right. So what it is, the theory with this now behind it is the idea that a line tangent, oh, it's still pink, that's an approximation, which we've been doing. The whole idea with the Euler's method is that this is a better approximation because it keeps us closer to that curve for a longer period of time. I'm not going to squeeze that word in there, so I'll smash it. It's a better approximation method for approximating values on our curve. Think about now, like if I wanted to approximate, go black again here. So let's say the value of 1 is right here. Well, here's the red line. That wouldn't be very close to the black one. If I did the green one, that's a little bit closer, but the pink one at 1 would have the value that's the closest to the functional value that we would be looking for, okay? So what we're really doing is stringing together a bunch of lines. The first one is tangent. The lines after that have the same slope, but they're not necessarily touching the curve anymore. They're just going in that same direction, okay? So here's how this is now going to play out. It's a little messy, and you typically do need a calculator, but for the sake of time, I have all these calculations so that we can save a little bit of time with these. What I want you to do is says find the first 3 approximations. So that's why we have y sub 1, y sub 2, y sub 3 using Euler's method, which just basically means 3 different lines we want to come up with for the initial value problem that's shown below. So here's our derivative. Here's our initial point where we're tangent to our curve. And then we're going to start at that x value of 0. Our dx is going to be a 0.1, okay? So what I want you to kind of sketch real quick, just so you understand what's happening in this problem. We are tangent to the curve at 0, 1, so it's somewhat similar to the one that I just graphed. And then draw in a curve that looks like this. We have a line tangent to that curve. That's kind of our basis of this that we're going to start off with. But again, we can see the red line gets further and further away from the curve, so we'd like to not stay on that red line forever. Otherwise, it's a terrible approximation technique long term. Okay, so the way Euler's method is now going to look, we're going to write this similar to our linearization. Oops, don't put the tick mark there, sorry. Do not want that. What I want is a subscript, so we want y sub 1. So this is going to give us our first y value in our approximation. Think about our linearization from above. So we want our functional value, so whatever the original functional value is, I'm going to call that y sub 0, plus our derivative value. So I'm going to write this as my derivative at whatever point we started out with. And then what we're going to be multiplying by here, for right now, you're going to put this little dx. And I'll explain a little bit here what the dx stands for in a second. So what we're really doing right now, if I want that first approximation, we're going to take the original y value like we would normally for our line, and that's going to be 1. And then we would want the slope at that point. So here's our slope anywhere that we want it. All right, that's our derivative. That's what this does for us. All we need is the y coordinate. Our slope is always 1 plus y. Well, the y at the initial point is a 1. So to figure out that slope, we're going to do a 1 plus a 1. Here's why we're going to use dx as a 0.1. Here's what we don't want to have to do every single time. So here's what this now means. The x coordinate that we are currently at was 0. Okay, that's the x coordinate at our point of tangency. If I tell you to move over 0.1, notice how the new x coordinate is going to be a 0.1. That's our difference in x. The one that we're at is 0. And if I move over 1/10 of a unit, my change in x is going to be a 0.1. Okay, so what that now gives us is this idea that if I go ahead and take the original y value, take my slope, multiply it by the new x coordinate, or the change in the x from the original to the new one, what I now get is that on the red line over here at where are we at? So 0.1, let's say this is 0.1, my red line would now have a value of 1.2. All right. What we're now going to do, though, we don't want to stay on the red line. So this is now when we talk about how let's take this new point and let's write a line that would have the same slope at this x coordinate, but it's going to keep us a little bit closer. So the way we're now going to do that is you're going to call this now y sub 2. Maybe black again. Understand what point we are now at. Our y coordinate is 1.2 when the x coordinate is a 0.1. I would strongly recommend marking this off to the side as we go through these. We started at 0, we moved over 1/10 of a unit, so now I'm at 0.1, and at 0.1 on that line, my y coordinate's a 1.2. So now, to find the second y coordinate, we're going to take, let me write it in its entirety now. We want to take the previous y value, the y value that we just got, find the slope of the curve at our new point, and then again, multiply it by our change in x. So the second approximation. So understand, this should now take us over here to 0.2. I'm going to take that previous y value, or the new y value of 1.2. I want to figure out what is the slope at that x sub 1, y sub 1 point. So at this point, what's our slope? Again, our slope in this problem, we just need the y coordinate. So it's 1 plus 1.2. And then multiply that by your change in x. Because what's really happening with this change in x, if we wrote line tangent, wouldn't we have x minus 0.1 right here? Well, if I moved over a 0.1, isn't my new x coordinate, if I can get my eraser to work, a 1.2, a 0.2, and then isn't that difference still just going to be this 0.1? So we're really just multiplying by that dx every single time. All right, so let's change that to 0.1. If you're good with decimals, feel free to do that in your head, on your paper, whatever. Again, I usually would have you go through this and make sure we can get all these, but you should get 1.42, I promise. So what that now has given us is our second approximation. We want one more. So what we are now at is an x coordinate of 0.2 and 1.42. So we're now on the pink line. If I could pull that pink line in over here. And we just found this point to be 1.42. And now we're going to do a new line at that point that has the same slope of the curve at that x coordinate. So our third one, this should be the one that we're looking for right now. You're going to take, and again, you don't necessarily have to write all of the subscripts initially, but since this is our first one, we want the y sub 2 point. We want the slope at that new second point. and then multiply it by our change in x. So our third one should be y sub 2. So y sub 2 is this guy. This is the y coordinate at that second point that we just found. So 1.42. Plus our slope at that point. Our slope is always 1 plus y. The y at our new point is that 1.42. And then again, we would have gone from 0.2 to 0.3. So the change in that interval would have still then been a 0.1. So what y sub 3 would now equal, and again, you can throw that into the calculator there, should give you 1.662. Similar to when we do lines tangent, actually, let's do this first. Understand what this now is. At x equals 0.3, we now get a value of 1.662. And then what I was saying is similar to when we did lines tangent, the way you would be expected to answer this, what we have just approximated is what the function value would be. So if I go back to this graph here, the black graph, we don't know what it is at 0.3, it's somewhere up here, but using these lines and stringing them together, we've just approximated that the functional value at 0.3, we would have to use this approximation symbol just like we did with lines tangent, is 1.662. Okay. Now, don't see when people are in class, I can hear them flipping their papers already. Don't flip your paper just yet, all right? Because what I want you to now do is let's find the real value. Because if that's our approximation, let's find the real value of 0.3. And the only way we can do that is what we quizzed on yesterday. If I know my derivative is 1 plus y, which we do, because I gave you that right here, then if we could find the original curve by separating our variables, so take that 1 plus y, divide it over, set that equal to the dx, we can actually find the original curve through the antiderivative. So on the left side, you're going to get that natural log absolute value of 1 plus y. On the right side, you're going to get the x plus ac. To figure out what our c is, we have this point right here, that when x is a 0, y is a 1. So let your y be a 1. When x is a 0. So what we get is c is the natural log of 2. So now write that equation in its entirety. So hopefully I can squeeze this in. So now I can go ahead and write this as the natural log, absolute value of y, or 1 plus y, would equal x plus the natural log of 2. Our goal is to solve for y, so we want to get rid of the natural log. So use your e to get rid of that. And then now we're going to start dealing a little bit more with these absolute values and understanding what this now, or how this changes our problem a little bit. So leave that, still the absolute values there, 1 plus y. We now have this little algebra trick that we've been dealing with where if this is my exponent, then what we really have is the e would have been raised to a power of x, and it would have gotten multiplied by another e raised to the power of 2. That's why we would have added those exponents together. And then understand that e to the natural log of 2 is just a 2. We would be multiplying it by an e to the x. Now really think about what absolute values mean, right? Like if I gave you, let me do it over here so I don't take up too much room. Doesn't the absolute value of 2 have two different possible solutions? It could be a positive 2 and it could be a negative 2. Both of those, if I took its absolute value, will give me a 2. So when I now do this, what y plus 1 could equal is either a positive 2 e to the x, or y plus 1 could have also equaled a negative 2 e to the x. The way we know which one we are dealing with is, again, I've been doing a lot of the circling of this point, so I'll recircle it, is this point right here. which one of these two options, so option number 1 or option number 2, if I plug in a 0, so let your x be a 0 here. If I let x be a 0, and then I solve for y, that's the one that's going to give me a 1. If I come to this one and I let this be a 0, wouldn't this give me a negative 2 on the right-hand side? And if I did 1 plus y equals a negative 2 and then solve that for y, that y is a negative 3. So that's why we're not dealing with this one. That's why we can eliminate this thought. And then this has to be the one that we're working with. But take that into account. If I would have told you that y of 0 equals a negative 1 up here, then you would have been dealing with this guy versus crossing it out. So that's important. Those absolute values actually give us two different solutions. We need to know which one we're working with. Okay. Now, since I have run out of room, I'm actually going to erase this because we still have 2 more steps. All right, solve that equation for y while I erase this. So the one that we're left with, go ahead and solve that for y. So get the y by itself. I try to erase. Oh, there's more room there. And then we should have our equation. And then if you have a calculator, our whole goal with this now is let's get the real value. So once we have y to equal 2e to the x minus a 1, that's our equation. Now let's actually plug in this 0.3 that we had over here and find out what our real value is. So if we now did 2e to the 0.3 minus a 1, and again, I already did this. If you wanted to check, make sure I'm not lying. When we throw that into our calculator, that gives us a value of 1.6997. This is the real value. This was the approximation value, so you can see that they are very, very similar to each other. All right. Hopefully you're able to squeeze all of that in there. All right, so now let's go to the next page, and then I try to write this so this now hopefully all kind of makes some sense. So 2a is our old idea. I want you to use a line tangent to estimate the value of f of 0.6 if we start at the x value of 0 with a y value of 4, and then this is our slope. So this is an old idea. We want to write a line tangent. So we're going to do y minus 4, because that's the y coordinate of our point. Our slope we'd have to calculate real quick, but it's pretty simple. It's the y coordinate minus 2. Our y coordinate is 4. So we would get a slope of 2, and then our x coordinate is a 0. So that's our line tangent. If we solve this for y, we get y equals 2x plus a 4. So from there, go ahead and evaluate the line value at a 0.6. And the value of the line at 0.6 should be 5.2. The way we present our answer, since we're estimating the value of f of 0.6, we write it as such that f of 0.6 is approximately 5.2. So the theory behind this is a line tangent is a nice way to approximate it, but Euler's method is a better way to approximate it. It keeps us closer to the curve for a longer period of time. So now when we go to B, we better get a value similar to this. Okay, it's just a different way of approximating it. So for letter B, you're going to use Euler's method. We're going to move over 2/10 of a unit each time, f of 0.6, and then f of 0 equals 4. So notice one little difference here. Here I told you how many I wanted. I wanted you to get y1, 2, and 3. I tell you find the first 3 approximations. I don't tell you how many to do here, so you just have to have some number sense. You need to understand that we are starting at the x value of 0. And starting at 0, my step size is going to be a 0.2. So I'm moving over 2/10 of a unit each time until I reach the x value of 0.6. So if I start at 0, move over 0.2 until I get to 0.6, then we are again doing 3 of them. All right. So that's our process. So for the first y value, we're basically using all the initial information, our initial y value, our initial slope, I just write this as the slope at this point, and then multiply that by our change in x. So the initial y value was the 4. Our slope is y minus 2, so that's 4 minus 2. And then we're moving over 2/10 of a unit each time. That, when we simplify it, should give you 4.4. The point we are now at is 0.2 comma 4.4. So to get the second one, so I'm going to stop writing all these little subscripts. We're going to go right into that second approximation. Now to get the second one, we're going to use all of the y sub 1 information. So the y value at y sub 1 is 4.4 plus the slope at that y sub 1 point, and the slope is again y minus 2. So my new y value is at 4.4 minus 2, and then my step size is 0.2. So that second y value, when we add all that up, multiply it all out, clean it all up, should give us 4.84. And then my new point, we're now at 0.4, the y coordinate is 4.84. The next one should be our answer. I'm going to give you a minute here, see if we understand where all this is coming from. So go ahead and write y sub 3, and let's make sure we know where these things should come from. So write down what you think comes next.
Should y2 equal 4.84 or 4.88?
I get 4.84. Do you get 4.88?
I got 4.84.
All right, hopefully we're right, Carter. Let's see. Because this is what, 0.44? So then I get 4.
I see where I went wrong. We're supposed to go 4.4 minus 0.2 or minus 2?
We're plugging into this right here. So so minus 2. Okay, so 4.84 is correct. I think it is. I'm pretty sure it is. Okay, yes. I'm second guessing myself for a second, but I do think that's right. I did just do it this morning, but.
So then you would do the 4.4 minus 2, which would be 2.4.
Correct.
2.4 times 0.2.
Correct.
And I'm getting 0.48 for that.
All right, let me check. 0.4 plus 2.4 times 0.2. Now I do get 4.88, so maybe you're right. Sorry, Carter, we're wrong. I was like, man, as soon as Carter agrees with me, I gotta be right. But I get that also, 4.4. And 2.4 times 0.2. Yeah, so let's go 4.88. That means my next one's going to be off just a little bit. So now, yeah, if you were going off of mine, we got to adjust a little bit. So we should have had that y value that we just discussed. And then you do that 4.88 minus a 2, and then times 0.2. So this one should be our answer. So now let me see what we get. Plus 2.88 times 0.2. All right, now I get 5.456. Okay. Now, write that answer correctly. We are approximating a functional value at 0.6. So we would say f of 0.6 is approximately 5.456. So that's the answer to that one. Compare them, because these should be similar. Notice how this is 5.2, this is 5.456, so we're certainly close. And what I wrote on the front page is, this is an approximation, the line tangent. Euler's method, in theory, should be a better approximation, because we're staying closer to the curve. So now, when we go to letter C, it will be revealed which one is the better approximation. Because now I want you to find the real antiderivative. So, or the real actual value. So we're going to say dy dx, our derivative, what was it, y minus 2. So we're going to separate those like we did earlier. Do your antiderivative of both. We get our natural log. And then x plus c. We can plug in our point. The point that I gave you, the starting point, the point where we're tangent that we know lies on our curve is 0, 4. So let your y be the 4. When x is a 0, and what we get c to equal is the natural log of 2. So then I'm going to go ahead and rewrite this equation. I got the natural log, the absolute value of y minus 2 equals x plus the natural log of 2. Looks very similar to the last one, where we're ready to now use your e to get rid of the natural log, leaving us with the absolute value bars around x equal, or x minus, or y minus 2. If you're not realizing at this point yet, we have to understand this little shortcut, the idea that if I have e raised to a sum, that we can break that down into two separate exponential functions, one raised to the x power, and in this case, the other one raised to the natural log of 2. So absolute value of y minus a2 equals 2 multiplied by e to the x, just like it was before. What this now means is y minus 2 could equal a positive 2 e to the x, or it could have equaled a negative 2 e to the x. The one that we know is going to be our answer is the one that when I plug in an x value of 0. Actually, let's do one more step to make sure we understand this. Let's add this. Yeah.
I got called in to leave early because I got to go to the doctor's office. Is that all right?
Yeah, go ahead, Alex.
All right, thank you.
All right. And then let's add the 2 over here. So the reason we know that we're going to be dealing with this one as our answer is because this is the one, if I let the x be a 0, it'll spit out a y value of 4. If I let this x be a 0 in the other equation, I'm going to get a y value of 0. All right, so that is why we're ultimately going to ignore this one. Now go ahead and plug in that 0.6. This is not an approximation. This is going to be the actual value that the function has at 0.6. But should be pretty darn close to the values that we were getting up here. So when we now do that, we get y of 0.6 to equal, I didn't mess this one up, I get 5.644. That's an ugly 5, so I'm going to rewrite that. So if this is the real value, which it is, when we go to look at these approximations, by staying closer to the curve, this one is a more accurate way to approximate this value than what we would have gotten up here with that 5.2. Okay? Okay, real quick, we'll probably only get through number 3. I'll give you a minute or two. See if you can decipher that. See if you understand this. The next page is an old AP question. These are very, very common because they go nicely with the slope field. Letter B is an Euler's method. Letter C is solving the equation, all the stuff that we've been doing. So we don't get to that. That's great. That's fine. But number 3, I just want to make sure we can leave here understanding how many do we need to do, and do we know where all these moving parts go? So take a minute or two and see where we get with this. Eventually you get to be pretty quick with these because there's obviously a pattern that starts to happen. People can get through these pretty quickly. So unless I screwed this up, 0.22, if you finish, I believe you should get this.
That's what I got.
All right, good. Carter got it, so gotta be good. Gotta be good. Which is good, because that means we're kind of understanding where all this is coming from. So people are wrapping up, we'll get going. Y sub 1 should be set equal to the original y value, so that's what this gives us as a 3. Then we would want our slope at the beginning, and it's y minus a 1, so in this case 3 minus a 1. Our step size is now a 0.1. So that first y value, we evaluate that, should have given us a 3.2. And then we know we're now at 0.1. And then our y coordinate is 3.2. What we would have talked about, if my step size is 0.1 and I need to get to 0.2 from the 0 value, we only need 2 of these. That's why this one can get done pretty quickly. So the second one should be our answer. So we want that new y coordinate of 3.2 plus our new slope, which is the 3.2 minus a 1, and then multiplied by our step size of 0.2. And then when we multiply all that together, combine like terms or combine the values, that's where we get that 3.42, but we want to make sure that we write it in that function notation. All right. All right, so real quick though, just go to letter B in this one. We won't go too extensively through all of this. You can do a slope field on this. It's x times y over a2. You can do that. But the reason for letter B, so let's do B real quick. Because there's one thing I want you to see to make sure we understand why something I'm having you do is important. If I want to use Euler's method, we're starting at 0. Our step size is 0.1. We're going to go to 0.2. So what we just did, we need 2 of these. So our first y coordinate we're going to get from right here is a 3. Now our slope is x times y divided by 2. So the x in this point is a 0. The y coordinate is 3. And that's how we're going to calculate that slope at that point. X multiplied by y divided by 2. Our step size, 0.1. Well, since that 0 is there, it works out nicely that we get the y sub 1 to be a 3. Notice how now your derivative of those has x and y in it. That's why it is important, and this is the first one where it's happened, where we want to now be keeping track of not only the y coordinate that we're coming up with, but also of the x coordinate. We want to know both of these, because when we now go to do this next step, the second one we use step number 1's information, so that had a y value of 3. When we now go to calculate this slope, I need to take x times y, and we're doing it with this new point over here. So it's got to be the 0.1 multiplied by that 3, and then that gets divided by a 2. So that's why I strongly recommend keeping track of these, because there's plenty of derivatives that have both x's and y's in them, and we need to make sure we know what both of those are as we're going through these steps. And when we do this, we get what? 3.015. So really common free response question. You can see how these get set up. We're not going to go through it. We've already done a few like it. But if you look at letter C, they're now asking you to find the real value. So you're going to have to separate your variables, do your antiderivative, plug in the 0.2. It'll give you the real value, and it should be close to that 3.015. All right? Okay, so we kind of finished. We got enough of it done to walk out of here feeling that we're not behind. Okay, so that's it. You're less than a minute. If you have any questions, feel free to hang out in that minute. But otherwise, get out of here. We'll see you guys tomorrow. Okay. Stop this.